Hey guys, this is Mr. Bell. Welcome to your first AP Environmental Science screencast. The purpose of these screencasts is to sort of fly in the face of the traditional model of teaching. That is, where students sit passively in class taking notes while the teacher lectures. I will certainly be using the lecture method in class. I do see the merits of it. However, I want to sort of minimize it by creating a modified flipped classroom where actually you guys go home at night and you learn the content on your own, and you do so by watching screencasts, which are my lectures recorded online. This way, it sort of frees up our class time together so that you can actively engage in the material and the content and hopefully bring a little bit more meaning to the learning process through hands on experience. Anyway, so our first screencast revolves around geology and geomorphology. Yeah, so we thought we'd start with the Earth today, and it makes sense. We want to sort of paint a picture of the physical setting and see where the Earth actually came from. What is it made up of? What is its structure? And how is it changing? So that's really what geology is. It is the study of the Earth, its structure and composition. Geomorphology is a sub-study of geology which examines landscapes and explores how they change over time. And usually these landscapes change as a result of both internal forces as well as external forces. The internal forces speak to the heat within Earth. Right, so we're talking about, of course, the theory of plate tectonics. We're talking about volcanism, earthquakes, and mountain building events. These forces are defied by leveling forces or destructive forces, forces of weathering, erosion, and deposition. So before we get into those geomorphological processes, we're going to start with the Earth itself and try to figure out where it came from, how was it formed, and what is its structure. So the prevailing theory in terms of how the Earth was formed centers on the Nebular Hypothesis, which postulates that the Earth and the origin of our solar system can all be traced back to the explosion of a supergiant star. When I say supergiant, we're talking about a star that's perhaps 100 times more massive than our own sun. These supergiants they're the rock stars in our universe, and they end their evolutionary sequence in a massive explosion. So tumultuous events mark the beginning of our solar system. And with the explosion of this supergiant star, there was an enormous amount of cosmic debris just sort of expelled out into empty space. And obviously, this material, this gas, dust, and debris, was forced outwards. However, simultaneously, gravity sort of brought it back in and compressed it. And ultimately, what was left was a vast cloud, and this cloud is known as a nebula. And nebulas really are they're like star factories. It's where stars are born, and of course, our own sun formed at the center of this nebula. As the material compressed and condensed at the center of it due to gravitational forces, it created pressures and temperatures that reached a critical mass to allow nuclear fusion to occur. And of course, nuclear fusion is a process, an energy driven process that forces the nuclei of lighter elements like hydrogen combining with other elements and nuclei of hydrogen to form heavier elements like helium. And in this nuclear fusion, it releases an enormous amount of energy as well as light. And therefore, at the center of this nebula, our star was born. About 99% of the material in this nebula went to the formation and went to the mass of our own sun, leaving 1% scattered around it. And that 1%, while paling in comparison to what was within the sun, was a sufficient amount of mass to build the 8 planets that now currently revolve around our sun. And this occurred sort of like the way that dust bunnies accumulate, beneath your bed. So as they revolved around our sun, because they had a sufficient angular velocity, that material started to build up. And these rocks and debris slammed into other rocks. And over time, these planetesimals, these baby planets, emerged as a result of these accretion events or these impact events. And over time, these rocks and planetesimals built up sufficient mass so that they actually exerted their own gravitational influence. And then more and more debris started to accumulate. And so ultimately, this debris went into the formation of our 8 planets, the terrestrial inner planets as well as the gas giants on the far reaches of our solar system. Of course, our own sun, our own Earth, was the 3rd planet from the sun. And as you can see from this rendition of what it must have looked like in its early days, well over 4 billion years ago, it was not a hospitable paradise. In fact, it was a large, massive, molten ball. And of course, the reason it was so hot and it was liquefied as magma and lava was because of those impact events. But also, some of the material that was incorporated into planet Earth was radioactive. And so a lot of this material caused the planet to sort of burn from within, and that created sort of an internal heat engine within planet Earth that is still continuing to burn to this very day. Over time, however, planet Earth did cool. And as it cooled, it started to separate. It started to become stratified. It sort of became like a nice lasagna, I guess. God, I love lasagna. I'm a huge fan of lasagna. And planet Earth is a lot like lasagna. The reason it's like lasagna is because it's layered, right? I make a pretty mean lasagna. I'm not going to lie to you. I make a vegetarian lasagna. I'll have my noodles laid out, some ricotta cheese. I'll roast up some red peppers, throw in some green peppers, a little spinach in there, maybe make a pretty mean vodka sauce. But nevertheless, this lasagna, and why am I talking about lasagna, is because it's layered, just like the Earth is. And each layer of my lasagna has its own unique characteristics, just like each layer within Earth's internal structure has its own unique characteristics. The Earth was cooling from the outside in. So as a result, we had a crust, sort of a scab that formed over the outer shell of the Earth. And then as you go deeper, you enter the area of greatest volume, which is known as the mantle. And then finally, getting deeper and deeper, we find the Earth's core. So as a result of this cooling and stratification, the lighter material, the less dense material, sort of migrated towards the surface. And since gravity pulls the heavier material towards the center of an object's mass, the heavier, more dense material accumulated at the core of the Earth. So as a result, if we're looking to label sort of the most abundant elements and where they're found, we're going to find the most abundant elements in the crust to be oxygen, the lighter material, and then at the center of the Earth, where the heavier material accumulated, we would find iron. So that's sort of how the material distributed itself as the Earth cooled. Oxygen was the most abundant element in the crust, the outer layer, along with silicon, and the heavier elements, namely iron, followed by nickel, accumulated at Earth's core. Now, to be fair, of course, this model is a bit simplistic, and we are going to dive into sublayers within each of these layers in the near future. Tomorrow we'll start to explore the crust itself and its major constituents. So that's it for today, guys. We'll see you tomorrow.